Okay, everybody. So today's talk is going to be an introduction to data-oriented design in Unity. So with today's talk, I just kind of wanted to kind of introduce the concepts of data-oriented design and show you a little bit about the development experience of using data-oriented design in Unity. So I'm going to be going over a couple code examples and then just kind of talking from my personal experience of using Unity dots for quite a while. And just kind of give you a little bit of an update about what the development experience is like if you do decide to use dots in Unity. So anyways, just a quick little introduction on myself. So I'm a Unity developer. I don't work for Unity. I'm completely independent. I do content creation on my YouTube channel called Turbo Makes Games. Over there, I do a lot of stuff mostly focused on Unity's data-oriented technology stack and their entity component system, a bunch of topics that we'll be talking about today. So I do like tutorials and kind of like news updates if there's any kind of new features coming to that, as well as just making like cool little showcase games to showcase what you can do with the technologies and all that. And because I've kind of been like come to be known within this like niche of Unity's dots, it's been leading me to get some like contracting and consulting type work. So I've been able to work now professionally with a bunch of companies ranging from all different shapes and sizes and stages of development for people who are kind of wanting to add more performance to their game or non-game application, things like that. So anyways, kind of diving into the actual talk here. So what is data-oriented design? So this is kind of the most kind of general way that I could figure about describing what data-oriented design is, where you're basically just making decisions about how to structure the data and transformations in an application that best fit how the computer stores and processes data. So as opposed to something like object-oriented programming, where we're creating these different objects to solve problems, we're really just kind of like focused on the data. How can we most efficiently store that data in the computer and process that in the CPU? So to kind of break down an example implementation of data-oriented design, this is kind of how I approach solving different problems using data-oriented design. The first thing I do is look at the input data. What is the data that we already have? Kind of what's our given data? So again, our input data. After that, we want to look at our output data. What's the actual thing that we're trying to change? So something happens within our game. Also very important to consider the scale of the data. Is this only just like one element of data, or do we have like many of these units of data? Because this is really going to influence, how we structure our data, how we structure our data and how we process that within the CPU. So when we look at actual data transformations, like how do we actually do this most efficiently based off of, again, our input data, our output data, what the scale of that data is. So these are just kind of like all the factors that we sort of need to consider when we're using data-oriented design. So to give a little bit more of a practical example, let's just say we're going to be moving 1,000 entities within our game world. So here we can just kind of break down, what some of our input data might be here. So of course we'd have, like the current position of our entity. This is going to be in a type of float 3. This is very similar to a vector 3 if you're just kind of familiar with regular Unity, but a float 3 is kind of a more efficient burst compatible type that they've created. We'll talk about some of these things a little bit later. And of course, the scale is going to be 1,000 because we're going to have each entity is going to have its own current position in the world. Next up is our move speed. So we figure that, each of these entities can have their own unique move speed. So maybe some can go a little bit faster, some could go a little bit slower. This is just a regular scalar floating point number. And of course, we have 1,000 of these because we're going to be, having one per each entity. Now let's say we have some player input. We want to give the player the ability to actually control all these entities within the world. So they can say, use the joystick to, move around all these entities in the game world. So the type of this is going to be float 2. Basically, we just kind of need the XY coordinates of where the joystick is. And the scale of this is only going to be 1 because, in this example, we just have, say, one player controlling all these 1,000 entities. Also, we're going to need delta time. Of course, if we just want to, normalize for frame rates, we're just going to have one instance of this delta time here as well. And then looking at the output data. So, what the thing that we're actually trying to change is going to be the end position, at the end of the frame, where is each entity going to be? Again, this is a type float 3, just an XYZ coordinate basically, and we're going to have one per each entity in the world. So kind of based off of this input data and output data, we can sort of consider, what our data structure is going to be like. So of course, the player input and delta time, these are just going to be stored as local variables that we can just use and kind of access from wherever. And then we need to be a little bit more efficient about how we're kind of storing the position and move speed. So we're going to store that in a structure of arrays. By the way, we are going to come back to this example, and I'm going to show you how to actually implement this in code here. Before we do that, I do just want to do a little quick point on SOA, which is structure of arrays. So the whole idea behind structure of arrays is we basically are storing these different data values within tightly packed arrays, but these are kind of like separate arrays. So we have like a separate array for all the position components associated with an entity, and a separate array for all the speed components associated with all the different entities. You will notice that these are essentially parallel arrays, meaning that say everything at element 0 of a given array is going to be, we can say associate that with one entity. So one entity is say going to be representative of this element 0, and that first element has the position and speed component associated with that. And then the next element, element 1 in both those arrays, those are going to be associated with a separate entity. So that's kind of how we can sort of keep track of these. Now, the main advantage of structure of arrays, this is something that you're going to see a lot of times in data-oriented design. The main advantage of this comes when we get into like SIMD programming, which is single instruction, multiple data, because it allows us to easily just take, say, the first couple elements of an array, store that into the actual assembly instruction. So we can basically process multiple things in just one single instruction. And that's what really leads to some of these massive performance gains that we can see here. So kind of orienting this discussion a little bit towards Unity Dots, we can talk about what it is. So Dots stands for the Data-Oriented Technology Stack. Basically, it is just a collection of packages based off of data-oriented design principles. So the kind of core package that we see is the entities package. You'll see this also sometimes called ECS. We'll be breaking down these packages in just a moment here. But we also have the C# job system, the burst compiler. There is their own physics, new physics library, and there's also the Havoc physics, because they recently kind of partnered with Havoc, and you can now do that through Unity Dots. They have a netcode for entities, which is kind of the data-oriented design multiplayer, which has been super nice. And there are more than these things. I do just want to point out that you can use these packages individually. You can kind of, pick and choose and kind of use these in your own, existing projects. But they really work best when you're using as many of them together as you can. They all just kind of like work hand in hand. So going a little bit more into detail on what some of these different packages are. So ECS, this is kind of again, the core package. I should mention that just kind of ECS as a concept isn't anything specific to Unity. It's kind of, like maybe a design pattern, I guess you could consider it. But Unity does have their own implementation of ECS, which is kind of known as the entities package. So yeah, basically the whole idea with ECS is it's kind of a separation of your data from your game logic. So when you think about ECS, the entity component system, it's not like one thing. It's not like, a system of entity components or something. It's more representative of 3 different things. So we have entities, components, and systems, and these are all kind of separate things. And this leads us to, do some really cool optimizations, as you'll see a little bit later. So an entity is just kind of like a thing in our game world. It really is just kind of like an association of data components, kind of going back to the SOA example. We figure, all the elements at, one particular, or all the data components at one element in an array, we can consider those all associated together. So they're just kind of, an association of data components. And we can be a little bit flexible about how we kind of determine what an entity is. So it can represent one thing, which is probably the most common. But one entity can also represent, say, multiple things or even just a small part of a larger thing. The only thing that an entity really has is just an index and a version number. And this is just a way to uniquely identify that entity in the game world. So next up, we have components, and these are really important because this is kind of the core, the actual data associated with our entities. Um, the thing about typically for these components, we wouldn't be using unmanaged data. So these are just simple types like integers, floating point numbers, booleans, things of that nature, because we know the actual like bit size of these particular types. So when we do that, we can basically store this unmanaged data inside what are known as chunks, which are just 16 kilobyte blocks of pre-allocated memory, which allows us to do some kind of more efficiencies that Unity takes care of. It also integrates really easily with the C# job system. Normally you can use the C# job system with regular game objects, but you do kind of have to like copy data over to native memory and then read that data back. So there's a little bit of overhead with that. However, when we are using data components in ECS, it integrates really easy. The data is already stored the exact way it needs to, so it allows us to do pretty easy multi-threading in most cases. Then finally, we get to systems. So these are the actual data transformations. So, taking our input data, doing some processing on that and converting it to the output data that we want. So this actually, modifies the data to make gameplay happen. By nature of the way that systems are created, basically just, us writing the system code, it'll just automatically, create that system and it'll start running within the game world. So we don't need to do anything specific to start it running. It's just going to start running by default, and it's going to run on groups of entities, which are called entity queries, which again we'll talk a little bit more in detail about later. I do just want to point out that systems by themselves, they are going to run on the main thread. However, they can schedule jobs that will go ahead and run on worker threads. So speaking of jobs, we can talk about the C# job system. So the C# job system, you may have heard of it. It's just a way to achieve multi-threading in Unity. The really nice thing about the C# job system is it really handles all the kind of scheduling and dependency checking. So this is a really important thing with multi-threading. So because there is always the possibility of a race condition where maybe we have one thread that's kind of like modifying some bit of data, and another thread is trying to like read to that same bit of data. So we don't know if the data had been modified, before or after we're reading it. So we just kind of like need to make sure that all the jobs are completing at the right time and everything, so that we get very deterministic results of when we're reading data, that the change data is going to be exactly as it's expected. And it's really nice that Unity kind of like handles a lot of that kind of like nitty gritty stuff for us. So we just, don't need to worry about it all too much. So the C# job system is best used for performance heavy calculations to be completed within a single frame. So I'd say this is a little bit different than say like async programming, where we might have say some like longer running work kind of running in the background. The C# job system really works best when we're like actually needing to complete some work within one single frame, but we still don't want to be blocking the main thread. Some reasons behind this is because, sometimes when we're working on entity data, we can't always guarantee that, when this job completes, if, we had some kind of input entities, we can't always guarantee that that input entity is going to exist once the job actually completes. So it is possible to have jobs go past the frame boundary, but in most cases, we want to be completing these jobs within one single frame here. So next up is the burst compiler. This again is another very important one here. The whole idea behind the burst compiler is it basically converts our our C# code down into native CPU code. We can actually see here, this is the burst inspector, which you can open up inside of Unity, and you can really see the whole disassembly of what the C# code actually breaks down to. So this is actually a code example that we're going to be looking at a little bit later in the video. where we're kind of moving these player entities through our world. And you can see in purple here, these are basically all the assembly instructions that the CPU is calling. So you see that there are things like vmul ps. So that P stands for packed, which basically means that it's packing multiple elements of data into that one single instruction call. So again, this kind of goes back to the SIMD, the single instruction multiple data. You also see v add ps. So it's again packing multiple bits of data into one single instruction, and we get a lot of really good efficiency gains from this. Now, the burst compiler, there are some kind of like restrictions on when and where we can use it. As long as you fit inside those instructions, in general, the burst compiler is pretty easy to use. You can just kind of like, tag some block of code, say, hey, I want this to be burst compiled. But for more advanced users, you can get like really in depth with it. Again, check out the disassembly, see what things are happening, and see if there's any ways that you can kind of like optimize what the output assembly is. So it is definitely a really excellent thing to have. And I'm sure you may have seen some of the results online about people using the burst compiler and getting these massive performance gains. So this is kind of how it actually does that. So now I want to transition to talk a little bit about the dots development experience. So we're going to start with a little bit of a code example. We're just going to go back to the whole thing about, say, moving 1,000 entities, where we can have this input data and output data. So let's kind of get into it here. So we'll start with creating a data component. So the data component that we're going to create here is a move speed data component. There are multiple different types of data component that we use, but we don't need to get into all those right now. This is just kind of the standard data component. You'll see that it is a public struct. We've called this move speed. The important thing that we're doing is we're implementing this iComponent data interface, which basically is just kind of like saying that this is the kind of standard component type that we're using. And you see that the only thing in this is just a public float field called value. The reason that I've called it value here is for data components where we just have a single field here. I call it value because it makes a lot more sense to say, when we're accessing this data, we can say move speed.value rather than saying like move speed.movespeed. The naming is just kind of a little bit redundant in that case. So yeah, this is basically just a data component. You'll see it's very simple. We don't have any methods on it or anything. Again, it's just kind of that separation of data from the game logic here. So just to show you kind of like how we might be able to actually set this data in the inspector, what we can do is create an authoring component. Now, an authoring component essentially starts with a regular mono behavior. You'll see that it is public class. We call this player authoring. You see it's inherits from mono behavior. And this basically just allows us to edit this field over in the Unity editor. So you'll see that, if we attach this to a game object, you'll see that we now have the ability to just modify this public field for move speed down here. Now, the important thing is if we have this game object in sort of a subscene, which is going to convert this game object over to an entity. Don't necessarily need to get too deep into that right now, but there's kind of a difference between regular game objects and ECS compatible entities. So this kind of conversion process is known as the baking process. So we have to use a baker to essentially look at the authoring components. And then from there, you see that this kind of last line, what we're doing here is we're saying, add component, we're adding to this new player entity that we've created. We're going to be adding a new move speed. And here we just set the underlying value to authoring.moveSpeed. So that's how we can kind of, have the ability to set things in the editor and have them reflected on the ECS side. Now, again, because this player authoring component is just a regular mono behavior, we can do all sorts of custom inspectors or editor tooling, anything that we need to with a regular mono behavior, as long as we're just setting kind of that underlying data in our Baker component here. So now once we have our data over on the ECS side, how do we actually process that? So the kind of easiest way to do that is by using what is known as an idiomatic foreach. So here's kind of just the general overall setup of a system. I probably don't need to get into this too in depth right now, A couple things that I do want to point out. You'll see that we're running this in on update, which is just, of course, a regular update method. So it's going to be running once every single frame. You'll see that I am burst compiling this method. So basically, all this stuff inside this method is going to be compiled with the burst compiler for the maximum efficiency. So before we even get into the loop, you'll see that I'm just kind of like getting my, the single unit data. So I have my delta time as well as getting my player move input, and then just kind of converting that over to a float 3 so we can easily modify the position. But really the important bit is this last bit down here where we have this for each loop. Now you can see that the air quotes collection that we're going to be iterating across is actually an entity query. So we're doing a system API.query to create our entity query. Essentially what this means is we're looking for any entities with a local transform as well as a move speed component. Now we do just kind of need to be careful about how we structure these entity queries, because this is basically going to return us everything in the game world with a local transform and a move speed. So this could be players, this could be enemies, this could be vehicles, just anything that has these particular components, we're going to be returning. Now we can get a little bit more granular with how we create these entity queries, so we can, filter for things that have specific components or are missing other specific components as well. So we can get, a little bit more granular to make sure that we're targeting the actual entities that we want to. Now, this system API.query, again, not only does it create the entity query, but it also gives us access to the data components so we can actually modify them. So you see on the local transform, I have this ref RW. That just means that we're opening up this local transform for write access. Again, this kind of goes back to the whole, job dependency checking thing where, we need to know what bits of data we're writing to and what bits of data we're just reading from. So the whole job dependency scheduling can make sure that we're, again, not overwriting any particular data or anything like that. But you see that basically we can just access the transform and the move speed via this tuple here. And, the actual work that we're doing is literally just one line here. We're just basically updating the position based off of our input vector multiplied by move speed multiplied by delta time. One other thing that I want to point out with the for each is that in this particular case, this is just running on the main thread. However, again, it is still burst compiled. Now, if we do want to actually multi-thread, this same work, we can create an IJobEntity, which is, one way that we can. This is kind of like one way that we can create a job struct, so we can multi-thread some of this different work in Unity. You see that here there are kind of a lot of similarities. We're basically creating a job struct, which is just going to be separate from our system here. We have our public fields for delta time as well as our player's input vector. And then down here in the execute method, this is where we're actually going to be doing the particular work on a per entity basis. So this line of code is essentially going to be running on every entity. The way that we kind of set the default query up in this case is by whatever types we pass into the parameters of this method. Again, looking for everything with a local transform and as well as a move speed. And you see I do have the ref and in keywords. Those are kind of like denoting, again, read and write access for the different data components. Now, us just creating this job struct right here doesn't do anything for us at all. We actually need to schedule this job. So the way we do that is, again, back in a system. You see that this, again, has some very similarities to the first system. Again, we're just getting our delta time, player move input, things of that nature. However, instead of like running that for each loop, we're creating a new player move job, going ahead and passing the values for the fields in there. And then at the end, we can choose how we want to run this job. So we can do a .run, which basically just runs the job immediately on the main thread, or we can do a schedule or schedule parallel if we want to schedule the job onto one worker thread or multiple worker threads. So, there's just a quick overview. I just wanted to show you a little bit of kind of the development experience and what some of the actual code looks like. Of course, you don't need to, really memorize all the details right now or anything, but do just kind of want to go over a couple, code observations. So you'll see that there is a clean separation between data and our transformations. So again, our data components are just, separate things. They don't have any, logic inside them. They're just kind of, regular raw data. And then our transformations, you can see that, those are completely separate. They don't have, yeah, I mean, they're just separate from the data components that we're iterating across. You will notice that there is some boilerplate code. We kind of have to do a decent amount of setup to get to like literally just that one line of code that is, actually updating the, position of these different entities. Because yeah, the actual work of the transformations are extremely simple, but there is kind of a lot of setup to kind of get to that point. So um, that can be one of the things that maybe is a little bit challenging earlier on in development is the speed at which you can kind of like get something to happen on screen is maybe a little bit slower than just in regular Unity. However, because this is a JetBrains talk, I do just want to give a quick shout out to some of the amazing dots tools that they've added into JetBrains Writer. So you can see when you're adding a new script, there's this new menu option for dots right here. And this pulls up basically another window here where we can essentially create, there's a bunch of templates for the different data components, systems, authoring components. So it really automates a lot of kind of that repetitive code and templatizes it out. And of course, JetBrains Writer is extremely powerful where you can create your own live templates and file templates. So I have a bunch of those created myself, and that has been a massive, massive time save for me. Just kind of, not writing a bunch of repetitive code. So that is something that has been extremely helpful for me. So I want to talk a little bit about, why I continue to use dots. Of course, performance is the kind of like main concern, main reason that most of my clients kind of come to me in the first place is because maybe they're creating some application where they're trying to do something a little bit more ambitious and they're, quickly running into some performance limitations. So I think, performance is kind of like the, almost like the hook, the reason that people start looking into, dots and ECS in the first place. But one reason that is something that's really important to me. One reason that I stick around is kind of like modularity. So the way because we have this separation of our data components from our logic and everything like that. Um, it leads to code that is much more maintainable in the long run. We don't have these like nasty web of dependencies where, a bunch of code is all, connected to each other. And then if we try to, rip something out or change something, then a whole bunch of things breaks and a bunch of things fall apart. Um, in my experience, it hasn't been like that as much where, there have been some times where I need to, recreate some larger portions of the application. And I've been able to fairly easily just kind of, rip those things out and replace them for something newer and better. Because again, there is that kind of like, separation. So, things are, just kind of a lot more modular. You can, pull things out, plug other things in. And it allows you to do some really cool things too. Like, for example, you can have multiple systems that essentially do the same thing, but maybe in different ways. And so you can maybe have like a designer, you can like give a hotkey to a designer that can like literally just like toggle back and forth between these two systems. So they can say, test out maybe multiple implementations of some different movement mechanics, like literally just side by side, just by toggling between the systems because they're going to be iterating across the same entities. So there's a lot of really cool things that you can do with it on that front. So if you are considering using dots, I do just want to kind of point out a couple things that you should consider. So not everything right now has an ECS compatible equivalent. So, you will be needing to essentially create a bridge between some of the things on the ECS side with things on the mono behavior side. UI is kind of a big one of these, as well as animations. There are some animation solutions from third parties right now. But, if you want to do it just kind of all through Unity, you are going to have to kind of, bridge the gap a little bit there. So there are separate physics systems. So if you are using the dots physics system, it's not going to interact with the regular Unity's physics system. The main place that I've kind of noticed this to be a little bit of an issue is with the XRI, the XR interaction toolkit, because that is all based off of the regular physics system. So if you are kind of using the dots physics system side by side with the XRI and the regular Unity physics system, you're going to have to again kind of do some things to make sure that things stay in sync, and you have to kind of manage two physics worlds at this point. So a little bit of things in there. It is still a bit buggy in the Unity editor, so when you click on things or it can be kind of difficult to like inspect the correct entity that you want, and they're just kind of like little things where like if you're like editing a field and you hit tab, like it doesn't always go to the next field. So it's like there's just kind of like some little kind of buggy things that they're still kind of working through at this point. Also, a major consideration is that the pool of developers to hire from are going to be a lot smaller than just kind of regular Unity. So it's kind of hard to expect somebody to have dots and ECS experience. So just kind of consider if you are using dots, they most likely are going to have to learn on the job. And then the last thing that I do just want to point out in the talk here is just kind of some learning resources for learning dots. So again, if you are kind of building up a team and wanting to point to some different resources, here's some good ways to do it. Real quick though, I do just want to say that if you are going into learning dots, you really need to have a good fundamental understanding about how computers work. Because again, if we're going to be optimizing for how the computer best stores and processes that data, it's really important to understand that at a good fundamental level. So you kind of know, like you kind of have an end goal of like the optimizations that you need to make. So, if you don't really have that understanding, it can be a little bit harder to see maybe some of the benefits of, why we're, going through a little bit of this extra trouble to, get a little bit more performance here. After that, you're going to need to learn some data-oriented design principles, which can be a little bit of a shift from an object-oriented programming mindset that a lot of people may have. And then on top of that, you do need to learn the dots API, which is going to be quite a bit different than just regular Unity game objects and everything like that. So I would almost consider this like pretty close to learning like a new engine or even a new programming language, just because there's so many different little things that you need to understand, and the way things that are done on the ECS side are just a little bit different here. As far as learning resources go, Unity has some fantastic ECS sample projects on their GitHub that are really great learning resource. I would highly recommend them. The ECS source code is also available open for inspection. So you can just kind of, F12 into whatever function and just kind of step through it and see what's going on in there. So that's been extremely helpful for me as well to just kind of, read through some of the ECS source code, see kind of what's going on behind the scenes. And I'm definitely like, pick up little things here and there. And then finally, YouTube, of course, is a great resource. My channel, again, Turbo Makes Games. I do a lot of kind of tutorial videos, and there are, definitely some other creators who are starting to make more ECS videos, as ECS is now kind of in its 1.0 production ready phase and everything like that. So a lot of good stuff out there online. So anyways, that's just about all I got for my talk today. Once again, if you want to check out my YouTube channel or Twitter, just go to Turbo Makes Games. And if you want to talk to me a little bit more directly about any projects that you're working on, you can hit me up by email as well. So thank you so much, everybody, for paying attention to the talk. And thank you so much to JetBrains for putting on this wonderful event here today.
Oh, I'm sorry. I was just taking some notes here. There's a lot of good stuff in this talk.
Sweet.
Yeah, I shared your channel in the chat, so folks definitely cool. Go check out Turbo Makes Games. A lot of cool stuff there. You had mentioned you actually consult for dots and stuff like that. An obvious question a lot of people who might be watching are thinking to themselves is like, how do you look at your game? How do you look at your application and determine okay, this is a good use case for using this technology to kind of get more out of my game?
Right, right. Yeah, definitely. I think like the first step is always like, if you have kind of a prototype existing already, a good first step is to just kind of look at the profiler and see, what exactly is going on. One important thing that I should mention about ECS is the optimizations are really geared towards CPU and memory efficiency. So it doesn't
Hmm.
actually really give us that much on the rendering side. So if you're kind of like, heavily GPU bound, then you might not get, some crazy results that other people are seeing from ECS and all that. I'd say in general, like kind of a way to look at some of the optimizations is if you're doing anything with like heavy calculations, but maybe not on like a large scale where you have like thousands and thousands of like data units that you're doing that on, then that might be a good candidate for just using the C# job system, just kind of stand alone. Because that's going to be, again, you can kind of like offload some of that heavy processing to worker threads and things like that. However, when you start to get to the point where you have, larger scales of entities, you want to have, more enemies, or you want to have a bunch of, dynamic asteroids or something like that, then that's where it starts to become like a good candidate for using ECS again, where you can kind of, parallelize a bunch of these, fairly simple kind of operations, things like that.
Yeah, the chat just mentioned, Thomas said he's making a narrative-based game, probably not a good use case for this kind of technology, right? I
Well,
mean
not necessarily, but again, kind of going back to some of the modularity aspects. Like if you want to kind of like use the advantage of the composition over inheritance, and you want to be able to kind of easily plug and play things for different behaviors. Just because your game doesn't use many thousands of entities doesn't mean that you can't use data oriented design for other things.
Yeah, that's a very good point. Something that was interesting kind of seeing your code samples throughout your slides. First of all, a lot of struct usage, right? So things are
Totally,
being
yeah,
stored on like the stack versus the heap. So that's really for memory efficiency. Things are
absolutely, yeah,
being passed by reference. So like you're not copying a lot of things, you're just reading from memory
right,
space.
exactly, yeah.
But one thing that kind of stuck out, I'd like to ask you, like, what if, as a naive dots developer, like that I would be getting into this, why don't I just slap burst compiled attributes everywhere and just kind of like win, right? Like, what's
Yeah, yeah,
what?
totally.
Yeah, like,
Yeah, so yeah, I mean, definitely you wanna use burst as much as you possibly can.
yeah.
Um, Again, I kinda hinted at this in the talk a little bit, but there are some restrictions around the burst compiler of, things that you can use it on. So, when you're looking at, like, managed data types where you're looking at, like, more classes or, like, traditional Unity components and things like that, we can't use the burst compiler on those. Again, this has to be all on unmanaged data, and it is actually pretty surprising, like, what you can accomplish by just using unmanaged data. Just kind of like, again, basic simple things like, floating point numbers, integers, booleans, things like that. But yeah, when you start integrating maybe some more existing Unity features, that's where you're not going to be allowed to use the Burst compiler. But yeah, totally use Burst as much as you can.
Oh, so I was being kind of like wacky, but you're saying go ahead, go wild and see what happens and just kind of like experiment. I think that's kind of what you're saying, right?
Yeah, yeah, totally. And then like if there's any restrictions or any kind of issues, you'll get a warning in the console, and then you can just with the kind of debugging experience, like it doesn't give you a lot of information for burst compiled code. So you typically will need to, temporarily disable the burst compiler, run your application again, and then you can get some better error messages to see, what exactly
Mhm.
is going on.
Yeah, I mean, I guess that brings me to a good follow-up to that. Like what are the drawbacks? So obviously you're compiling down to native code. Like, are you going to see slower compile times? Is it going to be harder to handle exceptions? Like, what are some of the drawbacks that you've seen using this approach?
Yeah, yeah, that's a good question. I mean, compile times are a little bit slower, but I mean, I haven't necessarily done any like really side by side comparisons or anything like that, but I guess like percentage wise, it isn't like much slower than just kind of like regular Unity compilation because that already takes a little bit of time. So it isn't like much more than that, but it is like a little bit of overhead during the compilation process. Again, as far as debugging goes, a lot of times you'll just kind of see an error in the console. It says like, this code was like compiled with the burst compiler, disable burst to get, better errors or whatever. So then you can just kind of, go up to the little burst menu, disable burst, run your code again, and then, it'll point you to the, specific location where you're getting that error from then.
Okay, very cool. Yeah, I guess one more question from the audience. Is there any good approach to connect dots with a regular mono behavior? Like, I'm not exactly sure what they mean, but maybe you understand that particular question.
Yeah. I mean, it's definitely something that you're going to need to do because, like I mentioned, ECS doesn't have or there isn't like an ECS equivalent of, everything just quite yet, and most likely there probably never will be. So things like this, again, that you'll see a lot of times with is, things like UI, where again, you kind of have to sort of bridge the gap between the ECS side and the, UI that you kind of have over on your game object side. Now, it isn't necessarily as straightforward as just kind of like, assigning references, because the way that ECS works is like most of the entities that you're creating, they're going to exist in what's called a subscene, which is sort of like a separate scene than your main game object scene. And Unity doesn't actually allow you to do any like cross scene references. So you can't just like drag in references in the inspector between, things in the main scene and things in the ECS subscene. So again, you kind of have to do a little bit of workarounds about, how from the ECS side can you like find things that are existing on the, mono behavior side, and vice versa, depending on what you're trying to do.
Okay. Yeah. On that note, Fedor, do you have any other questions, or
no?
I think we're good. Again, folks. Yeah. If you enjoyed this talk, definitely go subscribe to Turbo Makes Games. Awesome channel. Thank you so much, Johnny. This was a fantastic talk, and again, we'd love to have you back in the future. So,
I'd love that. Yeah, this was an awesome experience. So thank you so much for putting this on, and looking forward to a couple more of the talks that you guys got going on today.
Yep. Thank you, and we'll see you next time.
Awesome. Sounds
good.
See you guys.
Bye.